Moving on to our next speaker is Dann Smans, who's talking about modelling failure detection of lift doors through sensor fusion. Dan is currently serving as President Business Development for IoT and Digital Products at CDIS. He started with TK Elevator in one of the local branches and has been in leading positions across different countries for the past 10 or so years. His areas of special interest are digitalisation of field service and digital products overall. Thank you.
Already an applause, and I have yet to start. Well, thank you for the opportunity to talk to you all today. Modeling failure detection of lift doors through sensor fusion. I'd like to call out special thanks to 3 team members in my team. Guang Song, Jorge Roscoe, and Matt Fabina. They're data scientists in the team, and they're actually doing all the hard work, and I just get the pleasure to present it today. So what we'll cover today, what makes lift door a key area for lift maintenance, conventional approaches to lift door maintenance, so how is it done without digitalization, if you will. The increasing shift towards proactive with the Internet of Things has been a recurring topic for many years. I've seen in previous presentations, and I'll build on that. The concept of sensor fusion applied to lift doors, and then how sensor fusion can help make better informed decisions. And then questions and answers to wrap it up. So what makes lift doors a key area for the lift maintenance? Lift doors typically multiply with every floor. You have one controller, you have one machine, you have most of the time one of everything. Not always. Landing operating panel also repeats itself on every landing, but doors do as well. Especially when you have one with a front-rear configuration, it can even double across the height of the lift. Doors are also among the busiest parts of the lift. Typically they cycle open-close every time you use the lift. Ratio is not always 2 cycles on one ride. That is actually something we discovered over the past couple of years, is that parking rides actually happen more frequently, and then typically you don't have any door cycles. So that brings the average down. And then when it comes from a parking ride, it doesn't first cycle the doors before it leaves. It actually goes, but anywhere between 1 and 2 is a healthy number. Still, it's a very busy part. There are more door cycles than there are rides typically. And then subsequently, doors are among the top causes for lift breakdowns. There have been a number of studies on that already. One with Rory, actually, I think was last year or the year before. Yeah. When talking with customers, anywhere in the range of 7 out of 10 breakdowns are caused by malfunctioning door systems. That's what we hear. So the far and large majority is on the doors, not on the control system or the machine. Breakdowns do happen there. They can be quite severe when they happen there, but in terms of frequency, they happen mostly on the doors. That's why doors are so important from a maintenance perspective. If I send out a lift technician to do maintenance, I have only one machine to look at, one controller to look at, one of everything except the doors. They repeat on every floor. That's where my effort goes in. So that's why the doors are key. Now, when we look at conventional approach to lift maintenance, essentially the basic principles are preventive and corrective maintenance. Preventive is the lift doors or the equipment in general. It's no longer performing within its ideal operating parameters. It's no longer new, but it's within its normal operating parameters. It can do its job as per code requirement. And the regular preventive maintenance visits are really to inspect if it's still doing that and whether or not I need to take an action to keep that lift in good working order. Corrective is when something breaks, so it can no longer function, and then usually a repair or replacement is in order. Then preventive lift maintenance is really a process of routine examination most of the time, and then lubrication, cleaning, and adjustment. This is something where when you're a building operator and you talk with your service provider where there's a lot of misunderstanding in. Your guy comes, only looks at the lift, but what has that person actually done? Well, inspection is actually the key part of the job, and then when it's out of normal operating parameters, making an adjustment, a lubrication, a cleaning effort, or a replacement. And maintenance control programs is actually what steers that most of the time. Regulation around lift maintenance has been around for a very long time. The SME A17 code in North America actually in its first release in 1921 already had minimum standards for lift maintenance included. That's over a century. And the maintenance control plans used by the lift maintenance providers actually derive their activities they plan to steer to stay in line with the code requirements. So really, there were already general practices in place. They were transferred into codes, and the maintenance control plans were derived from that. Now, the thing with maintenance control plans is they're a universal checklist if you will. They don't take into consideration the specific requirements of each individual lift in its individual environment. And as we see specifically with doors, they're not used equally across the number of floors. Some floors have not been rented out or are not being used, so there are no door cycles. Whereas other floors, typically the ground floor or the first floor, depending which part of the world you come from, but the main entry floor has the most door cycles because that's where everybody gets in or out. So in fact, the maintenance need, the actual maintenance need, varies per floor. That again is not captured in a maintenance control program, but where it is really captured is when you go through making it more dynamic, more data-driven. Well, for that you need an infrastructure, a backbone to scale that up. And actually remote monitoring systems have been around for quite some time. In the 1980s, I believe Otis introduced their solution in 1988, if I'm not mistaken, Otis REM. And then many followed. All the major lift companies around the world have a remote monitoring system. And this really brought in data from the controller, from the lift controller itself, to help steer the actual maintenance need. The approach, though, taken is we already have a handheld diagnostics tool to interface with the lift control system. Why not just take that software that runs on there and put that on a gateway and leave that with the lift? Because the thing is, every lift model has its own tool, typically. So when you open up a lift technician's trunk and you look inside there, you'll see 2 crates and a toolbox. Now, the toolbox, we can all kind of figure out what it is and what's in there. The one crate is manuals for each and every lift. The other one is all the handheld tools that they need to carry to interface with the different lift system, because they all have different proprietary interfaces. And this really brought a lot of challenges with it as well. When you want to scale up this technology across a multi-brand strategy, so if you're a building operator or a lift company and you don't only maintain lifts from one brand, but from multi-brands, then how do you get access to that technology to actually interface with all these different controllers and make sense out of what they're all saying? There are lots of barrier in terms of compatibility with the type of connectors, with the software use, the protocol, the communication protocol, trying to convert that. So in practice, only a limited number of lifts were actually compatible with this approach. In fact, across most of the lift companies, we hear about a third is compatible of their portfolio with these type of solutions. And this is where we started seeing the introduction of sensor fusion in the lift industry. It started around the late 2010s, so 2017, 2018, the first ideas came out, the first products came out on the market. And really what was done instead is, let's try to bypass the lift controller altogether. Let's make use of sensor input data. Let's look at what data it gives and take a data scientist and a domain expert, look at the data and see what's actually happening, make that interpretation, if you will, of what is happening. And you can then apply the universal laws of physics. You are no longer working with pre-processed data that was needed to automate a lift in order for it to operate without a lift operator, which then was doubled to provide data for maintenance needs and insights in the lift, but you actually use data directly at the sensor edge. And you can overlay that data to make more reliable predictions, more reliable assessments, but also expand beyond areas where the lift controller doesn't provide you with data. Most of the times, lift controllers provide very limited data on doors, whereas we already assessed most of the effort is in the lift doors, in maintenance. So that is one way how you would resolve that. In this particular example here on the screen, we see a gyrometer, temperature, humidity, barometric pressure, and then more specifically light current technology that companies among Cetus produce, that they're well known for, which are really laser beams contained within the door opening to detect if someone is in the door opening or not. That's a very simple on-off type of application, but there's a lot more you can do with that data. Light intensity, for example, can give you the exact distance of the opening and the speed of what it's opening, down to a millimeter accuracy, for example. Now, this is a little bit hypothetical, conceptual, so let's get into a concrete example. I hope it's well visible on the screen. It's not as visible as here on the laptop. But in fact, what we see here, I'll stand here a little bit, then I can point to it a bit. So we see the light intensity at the top chart. And really what we see there is an opening and closing sequence of a door. That's the bell curve. And you can see that that bell curve, I mean, it's relatively smooth, but it's not 100% smooth, right? So there are some some things there, something, would it be noise, would it be specific to how this lift door is supposed to operate, is it something else? You cannot exclude it if you don't know what it is. If you have a very slow start or a very slow stop, as you can see those curves when they go from the top to the bottom, straight lines, it's not so smooth of a curve, so we don't quite know what that is. So let's lay over that accelerometer data in meters per second square. Then you actually get the vibration of the door panel as it is moving, and you can overlay on the same time frame what is actually happening. You can also overlay it with the velocity in meters per second. And what you see here, for example, is whether there is a door opening or closing. And we can even see from this third one whether it's a side opening or a central opening door. When you take a light curtain, it's essentially two sticks. One is a transmitter, one is a receiver. And if you put an accelerometer in both of them, then you can actually see which one is moving and which one is not. So if you have a central opening door, you would see curves on both of them. But here we see them on only one. So we actually know that it is a side opening door. With the direction of opening, we can even see if it's left or right opening. We don't even have to go to the lift in order to see this. We get it purely from the data. Again, we overlay that. So when you overlay that, also with the velocity in meters square, and it's actually the contours here are not quite visible, but what you would see is that all the data is overlapping, but that it's these end pieces in different colors. They're a bit hard to see from the back probably, but these small notches, that is where really the interesting stuff happens. If you have wear and tear on a door roller or the gibs are obstructed by dirt in the door sill, that is where you start seeing in the opening and the closing sequence when it's not building up its force or reducing its force, when there is something off. So this is how you can apply sensor fusion for door activity detection. Overlaying the different type of sensors, they really just cost a couple of quids each. They give you pretty reliable data, and when you overlay it, it doesn't really matter if one individual sensor is so accurate or not. The combined picture holistically gives you a very accurate picture. And you can do this on every sliding door. It doesn't matter what the make, model, or age of the equipment is. It really works on every sliding door. So the limitation that is introduced by the controller in its proprietariness, that is then lifted. And even if the controller would not be proprietary, which is more of a trend of the last couple of years, let's look outside. There are some 22 million lifts around the world. We're not going to upgrade all the controllers now just to get IoT, right? So we need something that is retrofittable and easier to install from a scaling perspective. If we apply that same concept to the right activity detection, then we can make it specific per floor, this analysis. What you really would not want to do is install additional hardware that gives you a very accurate positioning. Of course, the data is nice, but the effort you need to put in may not scale across an entire fleet of lifts. So you want to keep it accessible, also financially. So what you can actually do is if you take pressure, from barometric pressure, you can actually already get a very good reading on where a lift cabin is relative to the floor. We've been able to get it purely by these readings down to a 20 centimeter accuracy just by barometric pressure, actually in our solution. But it's still not good enough from our point of view. And why rely on only one sensor when you have more? So especially it's the drifting that you see, and especially when a cabin has been standing still overnight and not being used, it may drift into a area where it's, am I on this floor or on that floor? You're just not quite sure anymore. So when you put velocity against it, so when did I travel to which direction, and you detect that there is no further traveling since the last ride, then you can auto-correct the drifting. Once it says, okay, I'm no longer sure if I'm on this floor or on that floor, well, the lift hasn't moved, so we're still on the same floor that we last registered with. Then you actually can get a position in meter that by now we've been able to get almost within the landing zone accuracy of 20 millimeters up and down, respectively. I think it's 1/4 of an inch under the SME, if I'm not mistaken. So then you can actually get the positioning of the lift cabin. And when you then take that data holistically, you can actually see how are the doors being used on which floor, and where do I need to put my maintenance effort in. We've talked about the different building blocks of an IoT solution and how sensor fusion can make use of that. We've spoken about the data acquisition and then the processing of that data. using cloud technology and such as a backbone, but then you also have the user interface piece. So how do you bring this information to lift technicians? And there are a whole variety of ways how to do it, and I'm not saying this is per se the best one, but this is one form of doing it. This is a typical dashboard view, where, for example, here in the bottom, you could see a breakdown per floor, and then opening, closing times, trend vibrations, and so on. Again, there are many different ways how to do it, but this is how you could bring that information digestible to a lift technicians. They're not data scientists, so it needs to be accessible, that data. That also is needed for scaling to make this useful. So essentially, when fusing all the sensory inputs together, you can get a holistic picture of the door performance of the lift as a whole as well, but specifically the doors in this particular example. When you have the historical data over time, you can actually detect trends. So you can go more into the predictive realm. When combining the data science with the domain expert, you combine the people with the knowledge of what does this data tell me to what do I see in that data, what is actually happening, because I know the lift domain so well. And these actionable insights then aid the lift technician in making better informed decisions, what to do during a maintenance visit, without reducing the quality of service, which is key. This gets even more important when we look at the development of the past 10, 15 years. Typically, the units of maintenance per route, per technician, will be around 80 lifts. And within the last 10, 15 years, it has increased to about 120 lifts. And there are outliers, there are where it's more, there are where it's less, but this is the average that we see and hear about. Still the same lift technician who gets 50% more work in a course of just 10 to 15 years. So conventional methods just won't work, right? So that is where making better informed decisions can help you still facilitate the increase of number of lifts per technician without reducing the quality of service and having a better work-life balance, which also plays then into the health and safety aspect. So that's it on the presentation. Happy to take any questions, should there be any.
Okay, thank you, Dan. Any questions? No. I'm sure speakers will be very happy. One over here, sorry. I'm sure speakers will be happy to talk to you over coffee as well if you do have any other questions. So, who's Ludwig?
I just have a question about the door leaves. Would you install an accelerometer on every door leaf in the car?
A very good question. In our particular application, what we do is we install them directly in the light curtains, which are installed on the door panels of the cabin door. And what we are able to do is when the the cabin doors and the landing doors are connected through the clutch, right? That's when we can actually also pass on the vibration signature of that specific landing door onto where we have the sensor located, which is the cabin door.
And just to follow on that, these are all IoT devices that bypass the lift controller. So you
Correct.
You can independently.
Correct. Yes. Correct. Yeah.
Lovely. Thank you, Dan.